So great, thanks. I'm Kristin Woodley, and I'm a postdoc here at UCSC. And today I'm going to talk about how are certain ways that we can constrain the halos of early type galaxies, particularly elliptical type galaxies, using observations with globular clusters. So understanding the structure of baryonic and dark matter within galaxies is, of course, crucial to our basic understanding of how these galaxies form and evolve. And this is particularly challenging in early type galaxies, but there has been significant effort being pushed forth by a number of groups to understand the basic properties of these elliptical galaxies. And some of the main effort that's been put forth is by the ATLAS 3D survey, where they've obtained and probed stars within about 1 effective radii of 260 nearby early type galaxies. And a small handful of these galaxies have been probed out to about 2 to 3 effective radii by the Smeagol group and so on. But 1 effective radii, for example, only contains about 5% of the total mass within these early type galaxies. So to be able to understand what these halos are actually saying, or what these galaxies are doing beyond 1 or 2 effective radii, we need to push past that distance. And one of the ways that we can do this, and in some galaxies really the only way that we can do this, is using tracer particles. So for example, planetary nebulae and globular clusters. So in this particular presentation, I'm going to be talking about results that we've obtained from about 5 to 10 effective radii of a number of early type galaxies using globular clusters as dynamical tracers. I have no pointer, I guess. It's okay. So the bottom plot here just shows typically 1 early type galaxy in our sample, where the red circles represent the positions of our globular clusters. So globular clusters are excellent tracers in these types of systems because they exist in large quantities in early type galaxies. So we can build up large samples of tracer populations, but they also exist out to large radii. So in most cases, for our data sets, we have data that probes about 5 to 10 effective radii. So in order to learn about, oh, wonderful, thank you. Okay, so in order to learn about the halos of these galaxies, we don't want to learn about just one galaxy in particular. We obviously want to use an entire sample. So we want to be able to get a large number of elliptical galaxies, early type galaxies, that probe a range of parameters. So span a range of luminosity, but also span a range of environment. And of course, we want our tracer populations to be in large number out to large radii again, so globular clusters are perfect for this. But we also want to be able to include the shape and anisotropy parameters of these tracer populations. Assuming that these objects are spherically symmetric and they have isotropic orbits, leads to biases in our mass estimates. So we compensate for both of those in our analysis. So the survey that we're using is the SLUG survey, which Jean's going to talk about in detail later this morning, so I won't say much about it, except that it's a survey of about 25 early type galaxies within 30 megaparsecs from us. The galaxies do span a range of parameters or environment, which is perfect for our analysis. And we have wide field imaging, which we show here some images of these galaxies, but we also have follow-up DMOS spectroscopy, where we get radial velocity measurements of our globular clusters. So each of our galaxies have a few hundred globular clusters on average within them that we use as the basis for our dynamical analysis. So the main goal of this project is to be able to build up essentially mass profiles and dark matter fractions within these galaxies around 5 to 10 effective radii in galactocentric radius from the center of these systems. So we've chosen to build up our mass profiles using a power law distribution function methodology, where the globular clusters are our discrete tracers, which are described in a steady state and collisionless system by phase-space probability distribution function. And in particular, this model has some basic assumptions, and these assumptions are that the potential, the spherical halo potential of the galaxy, and also the tracer density of these systems are considered to be fit well by power laws. Okay. So we have 2 different distribution functions that we use within this methodology. The first one describes the tracer population as spherically symmetric, but we've also included a new distribution function which allows us to include flattening of our tracer population. So the models essentially just take the positions and radial velocities of our globular clusters, as well as our surface density slope as inputs. So here's one example of a surface density slope for our red and blue globular clusters, they're separated out by color. And we only constrain the mass profiles for all of our galaxies in the regions where the globular cluster population can actually be well constrained by a power law fit. So we ignore generally the inner regions and outer regions. So that's one more limitation to the model. So in the end, we have essentially 3 unknown parameters that we fit using a maximum likelihood estimator analysis. And this maximum likelihood estimator is constructed from the line of sight velocity distribution. We end up with the 3 parameters, the maximum likelihood fits, which are potential normalization and the potential slope, from which we get the mass of our galaxies as a function of radius, as well as the anisotropy, which tells us about the orbital motions of the objects themselves. So today I won't be discussing our anisotropy results, but if you're interested in those, come find me and I can tell you about what we find. So today I'm just going to be talking about their masses. So here's one example of our results. This is for one elliptical galaxy, NGC 4278. And on the left, I just show you our 1 and 2 sigma contour plot results for our maximum likelihood estimator. The red contours are for the red globular clusters, and the black are for the blue globular clusters. This is the anisotropy shown here. This is the potential normalization and the potential slope of the galaxy. So just to say one thing about the anisotropy results, you'll see that they actually, in some cases, do differ between the red and blue globular clusters. So we don't necessarily expect them to have the same orbital information. So since they exist in the same potential, we can use red and blue globular clusters as 2 different or 2 independent methods to obtain the masses within these galaxies. And because their orbits may not necessarily be the same, this is one way that we can potentially break the mass anisotropy degeneracy, which goes into these types of analyses. But in the end, we can constrain our mass profiles quite well within our galaxies. And on the right-hand side, I show a mass profile for the same galaxy represented as circular velocity for the blue and the red globular clusters as a function of radius. Here, our best fit model for the blue is a spherical distribution, and for the red is a flattening distribution. So they overlap within uncertainties, match quite well. This inner point here that you see represented by a star is the ATLAS 3D stellar results, where they have the IFU data that I mentioned earlier for the stars at 1 effective radii, which match quite well if you extrapolate our data inward. But again, we don't cover this region. Our globular clusters, as I shown earlier, do not follow a power loss distribution in that region, so we exclude it. So we can do the same type of analysis for all of our galaxies in our sample. Now, SLUGS has about 25 galaxies, but right now we've been able to do this method for about 10 galaxies. We will be including more galaxies as they get reduced and analyzed within our group's progress. But right now we have about 10 to work with. And on the left side, I show their mass distribution. So this is the total mass distribution that comes out of our maximum likelihood estimator, as well as their corresponding circular velocity curves. So at present, we are looking more closely at our circular velocity curves to understand and constrain what type or what range of lambda CDM cosmology matches our observations. But this is something that's currently in progress, and we hope to have results on this soon for each one of our galaxies. So one of the outputs to our models is, again, the galaxy potential. And I represent that here as galaxy potential slope. So the first plot I'm showing you on the left is the galaxy potential slope as a function of total mass within 5 effective radii from the center of the galaxy. And in past studies, this was a study that was done using the same type of distribution function methodology. And they found very tentative evidence that there may be evidence that the least massive galaxies for early type galaxies have the steepest galaxy potential slope. So if you look here, the dark gray bands are the 68% confidence range, where the light gray bands are 95% confidence range. And there is a slight indication that this may be turning downwards as you move to larger and larger masses. So we have done the same type of analysis, but now we've included our data is all determined homogeneously, where it's analyzed and reduced homogeneously. and also we have a larger number of tracer populations, and our new methodology allows for flattening of the potential, flattening of the tracer population, which is a more realistic representation of what's actually happening within the globular clusters. And we plot our results on the right-hand side. So these bars here just represent our 68% confidence range from our maximum likelihood estimator. And we see two things from this plot. The first is that we need stars and dark matter to be able to match our data. We cannot exclude dark matter from these types of systems. And the second is that there may be more evidence or stronger evidence to see this increase or steeper potential slope at less massive galaxies. We can also represent this as the total mass density slope for our galaxies. The total mass density slope is an important quantity because it can tell us about the relative importance of various baryonic processes which happen within these galaxies and the dark matter responses to those baryonic processes. So we plot here the total mass density slope as a function now of stellar mass within our galaxies out to 5 effective radii. And you'll see that our values, again, these are the 68% confidence limits, range from around -2, which is an isothermal, to slightly steeper to around -2.5. The line that you see drawn through there is not a fit to our data. This is our fit to the SLAC survey data, which is 73 early type galaxies measured within 1 effective radii. And their data, the slope of that data matches quite well with ours. So this type of universal, if you will, total mass density slope that seems to be found in all early type galaxies extends out to at least 5 effective radii. This is also consistent with what is generally found in cosmological simulations for early type galaxies, but is not the same as what you find in clusters of galaxies. In clusters of galaxies, the total mass density slopes are much more shallow or shallower than what we find in early type galaxies. They're around -1.1, 1.2, which is more consistent with what slope you would find for cold dark matter only type models. But this trend that you see of increasing or steeper total mass density slope for less massive galaxies seems to be consistent for normal early type galaxies. We can also obtain more information using the total mass density slope. Remus et al. Recent cosmological simulations have indicated, actually found very similar results to what we find observationally within our slug sample of dynamically determined masses. They find that as you move to more shallower total mass density slopes, which corresponds to more massive galaxies, that, so they correspond to more massive galaxies and also to bigger galaxies due to the mass size relation, which we find as well, which I showed in the last slide. But they also find that more massive galaxies correspond to larger dark matter fractions, which is something that we find as well, and I'll show that in the next plot. Interestingly, they found in their simulations as well that these more massive galaxies, or galaxies with shallower total mass density slopes, have a smaller fraction of in situ stars compared to less massive galaxies. So that implies for our more massive galaxies in our sample that they build up a larger fraction of their stars due to accretion events, which builds up the outer halos of these galaxies. So if you were to take their values at face for our sample of galaxies that we have right now in our survey, this would indicate that the fraction of in situ stars for our most massive galaxies range from about 10 to 20%, and our least massive galaxies range from about 20 to 30%. And lastly, one thing that we can do once we have our total mass density or our total masses that we get from our models is to decompose them into both stars and dark matter. And I show you examples for 2 galaxies, NGC 4278 and 4365, represented as mass and circular velocity. With this decomposition, we can then look at the dark matter fractions within these galaxies as a function of radius. And at 5 effective radii, which our globular cluster system allows us to probe out to these larger distances, we find the dark matter fraction is around 0.4 to 0.8. And these more massive galaxies up here do have the higher or larger dark matter fractions within our galaxy sample. So just to conclude, we've used the slug survey, which consists of 25 early type galaxies, which again Gene will talk about in the next session. And we've applied our maximum likelihood analysis to 10 of them, using globular clusters as dynamical probes to the halos of these galaxies. And what we've been able to tentatively find so far is that it seems that early type galaxies, even out to these larger distances, are still represented by an isothermal profile. And also the least massive galaxies in our sample show evidence for having steeper potentials, steeper total mass density profiles, lower dark matter fractions, and according to simulations may have undergone less accretion events to build up their stars than more massive galaxies do. So we are obtaining more and more data all the time, and of course we're in the process of reducing and analyzing the remaining galaxies in our sample. So as these galaxies come in, we'll be including them in this mass analysis, and that will allow us to be able to probe some of these properties as a function of galaxy environment and other galaxy properties. So stay tuned for that. Thank you.
Question for Kristin. Okay? Go ahead.
Yeah. So you said you weren't going to comment on your anisotropy results, but you showed some. So it looked like for the red cluster population that it was weakly tangentially anisotropic, which seems unusual from the theoretical point of view. Perhaps.
Yeah.
So I wondered if you could comment on that.
Yeah, so for that particular galaxy, that red globular cluster system, that was the results for slightly flattened, whereas the blue was for slightly spherical. So if we look at the results for the bulk of the galaxies, we do find on average that our galaxies have consistent with isotropic orbits for both blue and the red. They move around slightly, of course, in that parameter space for each individual galaxy, but they are consistent with isotropic, which still is at odds with what you would expect from theoretical predictions, where you expect both populations, especially the blue globular cluster population, to be radial, have radial anisotropy. So there must be some things that are happening to globular clusters that take away from this radial anisotropy, dynamical friction, being destroyed by tidal shocks, and other events that are preferentially perhaps destroying globular clusters on radial orbits and leaving a more tangential or isotropic system. Yeah, we assume a constant beta. So what you would expect in reality is to find that perhaps as you move out to larger radii, the anisotropy would increase radially. But in the range that we're probing, our results are still not consistent with what you would expect to see from stars or halo populations, from at least what models say. But the results that we're finding are consistent with the results from previous observational results. They're yeah.
David, in the back.
Should data self-contained to explore the issue of whether bond is a possible explanation, or what, and if not, what would you need in order to explore that aspect?
I think we can check whether MOND and other. I think that we're able to check whether MOND is consistent with our circular velocity curves. I think we should be able to do that.
Have you explored that?
We're in the process of doing that for CDM, but we'll also be including MOND and other theories as well, of course. Yeah.
Anatoly, do you want to comment on that? Because you've done those measurements. No? Okay. Right? Rho going is R to the minus 3. Any other question? All right, then let's thank Kristin again.